The title of my talk is a Grobner basis for Schubert patch IDs. And just as a short introduction, Schubert patch IDs are basically prime dividing IDs of certain varieties. And Alexander Young gave a conjecture in relation to this Grobner basis result for this family of IDs. Primarily, what we show is that this conjecture is true using a technique called Grobner basis via linkage. So I'm just going to start with a baby example of this technique. So here we consider Grobner basis result for an ideal of maximum minus. So as an example here, let X be a 2x3 generic matrix and R be its coordinate ring, and G here be the set of minus of size 2, the maximum minus in this matrix, and I be the ideal generated by this minus. So what we wish to show in this example is that with respect to this lexicographic term order on R, where the variables in X here are ordered this way, that this set G forms a Grobner basis for I. And first, what we do is that from I here, we kind of obtain, in some sense, two new IDs, J and N. And then we observe that N is contained in the intersection of I and J. And while if you mod I by the ideal I by the ideal N, we get these two generators. And if we do the same thing for J mod by N, we get these two generators. And then we have this R by N modu isomorphism. So continue with this example. If we set A to be the ideal generated by the initial term of each minor in this set G with respect to the term order, lexicographic term order I said earlier, we got this. We set B to be the initial ideal of J with respect to the same lexicographic term order, and C to be the initial ideal of N with respect to that term order. We get this, and we observe from this all these settings we have this inclusion, and as a result we have this we can observe, we can see easily that we have this R by C modu isomorphism. And if I use so far the two isomorphisms I've obtained, the R by N modu isomorphism and this particular one, I'll have this equality of EBAT functions. And as a result, we're going to have this equality of monomial IDs, which basically gives the Grobner basis result by definition. Okay, so all the time, I said I mod by N is given by these two generators, and J mod by N is given by these two generators, and I claim I have this isomorphism. And just to see, like, kind of explicitly, if I define a map here that takes each minor in here to the product of this form, where this F here is kind of a fixed minor in here, fixed a particular minor in here, F prime can be obtained from that F. So for example, we fix this one here and then we kind of do a cut in here. We got X11 and that's X11 here, that's F prime. So that mapping actually gives the isomorphism in the sense that, as an example, explicitly, look at the first one here. Obviously this one, if you apply this here, we have this product. And then of course, this we call this and we have X11. But the second generator is interesting. When you apply the map to this, we have this product of this form here. And when you take the product of the numerators, this numerator with this minor here, we can express as a combination of these two here. And this particular minor here belongs to N, and it goes away because we are modding by N. And for these, it cut this away, and then we are left with X12 in here. Okay, that's by the way. So here is actually a lemma that basically kind of makes the previous example work so well. In other words, it kind of encapsulates all the steps involved in that example of an ideal of maximum minor, and is due to Gola, Miglo, and Nagel. So let I, J, and N be homogeneous ideals of graded algebra, however, if you K with this inclusion, and A, B, C are homogeneous ideals of R, they are monomial ideals with this inclusion satisfied, and B is the initial ideal of J with respect to this term order, and C is the initial ideal of N with respect to this term order. Suppose we can find a particular integer such that we have these vector spaces isomorphisms for all N in Z, then we have this equality, which basically talking about, gives us the Grobner basis result. And in our own work, we kind of use a multigraded version of this result. We use a multigraded, this is in a standard version, we use a multigraded version of this result. And here is the multigraded version, which is closely kind of similar to the other one, to the previous one, the standard one, just that here we're using a positively multigraded polynomial ring. Okay, so Now I'm going to extend the earlier example of Grobner-based result, the one I gave earlier for ideal of maxima minor. I'm going to extend that to larger classes of generalized determinantal ideals. And one of these classes that is of much importance to us in our own work is the Schubert patch ideals. Schubert patch ideals. Okay, so what is this ideal? Before I define the ideal, let me define the varieties that these ideals are coming from. So let G here denote the general linear group of invertible n by n matrices with entries in the field K, and B minus or be the subgroup of lower triangular matrices in G. For in our own work, we worked complete flag variety G mod by B minus. And given a variety in this complete flag variety, we set M subscript V comma X to be the intersection of this variety with this permitted opposite big cell. And K Newton actually call this variety X patch, while Insko and Young call their dividing ideals patch ideal. But for us in particular, we are interested in when X are Schubert varieties, and in that case, well, we call in that case when X is Schubert variety, we call M subscript V comma W Schubert patch varieties, and dividing ideals we call it Schubert patch ideals. So let's see some dividing equations for this particular ideal. So in here, this ideal is divided over two pair of permutations. So here we have V comma W here. So if we start with these, let me just kind of explain some parameters are here. W here is regarded as a permutation matrix, and W subscript P by Q here means northwest rectangular submatrix of W. We see that what that means in a moment. And this ZV here is a specialized generic matrix. It's full of zeros, ones, and variables, as you can see in this example. I'll also discuss that more in a moment. And then if you have all these here being said, what is Schubert patch ideal? So we denote it by Q subscript V comma W. It's just the ideal generated by the minus of size 1 plus this rank in this rectangular submatrix for all P and Q. And as a matter of fact, instead of just using all these pairs here, there's actually a smaller subset of these pairs that's just enough to generate this ideal. And this nice subset is what we call an essential set. And if you take a particular pair in an essential set and you obtain a minor from that particular pair, that minor is called an essential minor. I will explain more on that here in a moment. So now let's see this example. We have V to be 3, 4, 5, 1, 2. So here you come to column 1 and then you go to row 3, you put a 1 there for the specialized generic matrix corresponding to this V. And then here we have second column, go to row 4, you put a 1 and so on, 3, 4, 5, 1, 2. And for each of these ones, below each of these 1, you assign 0. And then for every other entry, you put variables there. And the index of each of those variables correspond to their location. So that gives us this part here. And then for the rank, we have the diagram for this W. We have a diagram here, the root diagram. And it's almost similar to this. What we do, so instead of putting ones inside this matrix, what we do instead, we replace each of the 1 with a dot. So this is 1, 4, 3, 2, 5, going row by row. And then for each of the dots, we kind of we kind of place a hook to the right of each of these dots and a hook below each of these dots. And every other kind of spot that is left, we kind of put boxes there. And this box is what we call diagram of this permutation. And here I talk about essential. I mean, right now we have three boxes in here. And out of these 3 boxes, only 2 of them kind of forms up the essential set. So as a kind of explicit definition for essential set, this box belongs to the essential set because if you look immediately to its right and immediately below it, there's no other box there. So we have only 2 of those. So how does this work? So basically, just go to an essential box, pick this essential box, for example. Sorry, pick this essential box, for example, then go in here, this rectangular submatrix, check the rank of it. The rank is actually, because there's 1 dot there, the rank is 1. And then we do 1 plus that rank, which is also 2. So we come to the corresponding rectangular submatrix there. We compute 2 by 2 minor in here. And that's what gives rise to this first 3 generator. And we come here likewise for this essential box. We have this done. We consider this rectangular submatrix The rank here is 1 as well. Then we compute 2 by 2 minor in here. And then we got these and these with other one that has already been done before. And again, just to repeat again, for each of, I mean, these minors are called essential minors because I use essential boxes for them. Okay. So let's see some results we had on this Schubert patch reduce. So as I said earlier, in a public talk, Alexander Young gave a conjecture, and here is the conjecture. He actually stated that the essential minors of Schubert patch reduce form the Grobner basis. So what we do is that we prove that this conjecture is true. And as a matter of fact, not all Schubert patch reduce are homogeneous with respect to the standard grading. And due to the way we structured our proof for this Grobner basis result for Schubert patch reduce, with little addition to it, we're able to show that the Schubert patch reduce that are homogeneous with respect to the standard grading is glitchy. And that's this result here. That is, they belong to the, I mean, the homogeneous ones with respect to standard grading belong to the Gorenstein liaison class of complete intersection. Okay, so let's see another example of this technique that I explained earlier that I used for the ideal of maximum minor. Now this time I want to use this technique on Schubert patch I do. So here, this is the other example I did the other time. You recall with these permutations, I have the specialized generic matrix here, and this was the ideal we had the other time. So here we set I to be this ideal, R to be the coordinate ring coming from this matrix, and G to be set of all essential minors and I. Again, we just want to show with respect to this lexicographic time order on R, where now we are holding the variable this way, and here we're giving preference to the variables in blue over the ones in red. We want to show that this set G forms a Grobner basis for I. Okay, just like before, again, in some sense, we obtain two new ideals from I, J and N, and then we observe that if we have this inclusion, N is contained in intersection I and J. And also when you mod I, this ideal by N, basically you're just modding this out here, and then we're going to have these two generators. And if you mod this by this ideal here, you have these two generators, and then we have this isomorphism here, R by N modular isomorphism. And if you set A to be the, just like before, the initial term of each of these minor here, we have this, and if B here is set to be the initial ideal of J, and C is set to be initial ideal of N. We also have this inclusion here, and we can also kind of verify that we have this R by C modular isomorphism. And again, just using this, using the two modular isomorphism I showed you just now, we will have this equality of Hilbert functions, and that also gives rise to this equality. And so we have the Grobner basis result by definition. Okay, so let's see another class of generalized determinantal ideal. So here we have rationalistic ideals, and just like before, so the dividing equation for this ideal is very similar to the previous ideal I talked about. Just like now, just that now we don't, for each of the ones that we have here in the specialized generic matrix, for each of the ones, below each of the one you assign 0, and to the right of the one you have assigned 0. So basically, all the variables that are actually read in the specialized generic matrix I did all the time, we turn them to 0. And then we do the same thing. So in other words, pick an essential box, find the essential minor, find all the minors there, pick another essential box, then find all the minors there. And if you do that, you get these generators there. And why am I discussing this? Because we could actually adapt our proof of the Grobner basis result for Schubert patch ideals. So the proof we gave for the Grobner basis result for Schubert patch ideals, we could actually adapt that proof, and then we could get an alternative proof to Wu Young's Grobner basis result for rationalistic ideals. And just like other ones, also, not all Schubert patch ideals are homogeneous with respect to standard grading. The same thing also here. Not all rationalistic ideals are homogeneous with respect to standard grading. And with little addition to our proof of this known Grobner basis result for rationalistic ideals, we're also able to show that rationalistic ideals, those ones that are just homogeneous with respect to standard grading, are glitchy. And then one more implication, and I will be done with this. So this is another family of ideal, Schubert determinantal ideals, with this dividing equation, also almost similar to what we did all the time, except for the fact that, except for that, in this case, we are using a pure generic matrix, not a specialized generic matrix, no 1 and 0 there. It's just purely generic matrix. And we do the same thing. So we come here, pick an essential box, Then we find the corresponding minor, which are called essential minors in here, 2 by 2 in here, because the rank of this is 1. And we'll pick this essential box as well, and then we'll compute the essential minors in here. And then we're going to have this here for this ideal. So let's see also some result we had about this. Actually, all of the results in here are just like known results. We kind of just saw that we can actually kind of imply that as well from our work. Okay, so here, this family of ideals, the Schubert determinantal ideals, they're actually special case of rationalistic ideals. And consequently, we also get an alternative proof to the known fact that the essential minors of every Schubert determinantal ideal form a Grobner basis. And in particular, since this family of ideals, Schubert determinantal ideals, since they are homogeneous, it follows that they're also glitchy, because the other time I said the homogeneous rationalistic ideals, they're also glitchy. And this glitchy result is actually not new. I mean, there's an existing paper that actually implies that, just that the proof from this paper relies on some combinatorial results. Okay, and as a future direction, so what we plan doing, we wish to use this technique, Grobner basis via linkage technique, to give a new proof of the Grobner based result for some type C rationalistic ideals. So this is also known, just that the proof that the author gave to it is kind of dependent on the characteristics of the ring, but we are hoping ours will not be characteristic dependent. Yeah, thank you so much.
Great. Okay, thanks, Emmanuel, for a very nice talk. Are there any, thank the speaker and ask, are there any questions? Okay, so if there's no further questions, let's thank the speaker again. And tomorrow we'll resume at 9:30 with our invited lecturer. Laura Escobar will speak at 9:30, and I believe Jenna is chairing the sessions tomorrow morning. So I look forward to seeing many of you tomorrow.
Sounds good.